Given an array of integers, find if the array contains any duplicates. If there is at least one duplicate integer in the array, return true. Otherwise, return false. Let's start by imagining this array of integers. Can you see any duplicates here? Well, we have the duplicates 2's and also the duplicates 3's. Since there is at least one duplicate, we will return true. So how do we code a function that takes in an array of integers and returns true if there are any duplicates in this array? Go ahead and pause the video to think about it. The first method I'll go over is called the brute force method. Brute force is just a term that can be applied to all problems. And it means that we're going to solve this problem in the easiest way possible. The trade-off is that it won't be a very efficient solution. And in this case, the brute force solution won't be efficient when we're given a very large array as an input. But it's okay to start with the brute force solution and work towards a better solution later. So let's look at the brute force solution for this problem. For every pair of elements in the array, check if they are equal to each other. If they are equal to each other, then you've found duplicates. So how do we check all pairs? Let's imagine that P1 and P2 store indices in the array. As you know, indices for arrays starts at 0. Currently, P1 is at index 0 and P2 is at index 1 in the array. Check to see if the array at P1 is equal to the array at P2. Let's keep shifting P2 over to the right by 1 in order to consider a new pair. Once P2 reaches the end, move P1 to the right by 1 and restart P2. Notice, P2 does not ever go behind P1, because if it did, then we would just be checking a pair that we've already seen before. Finally, the array at P1 and the array at P2 are equal to each other. We've found a duplicate, and therefore we can return true. So here's the code. It's in Python, but I'll leave a link below for a C++ implementation. However, take this time to pick up some Python and see how easy it is. Here's our function called hasDuplicates, which takes in an array called nums. This next line is saying that P1 will start at 0 and will go up to the length of nums. P2 will start at P1 plus 1 and also go up to the length of nums. This is nothing but a nested for loop. Next, we check to see if nums at P1 is equal to nums at P2. If they are equal to each other, then we return true because we just found a duplicate. After the nested for loops finish, we return false. Why? Remember, the nested for loops check all pairs of elements to see if they are equal to each other. And if we manage to check all pairs without finding a pair that is equal to each other, then we can rest assured that there were no duplicates. And so if we make it outside of the double for loops, we can just return false. Now that we know the code, let's look into the big O time and space complexity. Let's start by considering the worst case input array. The worst it gets is when we have to check every pair to determine whether or not there are duplicates. This happens when the duplicates are either at the very end or when there are no duplicates. So what is the big O runtime here? Remember, for every element, we check every other element. So it's O of n squared. And a big rule of thumb here is that whenever you see nested for loops, you should think about and consider O of n squared. Next, let's look at the space complexity. Remember, the extra space we're using is for P1 and P2. This extra space will not change in size based on the input array size. That is, no matter what the size of the input array is, we will always just use P1 and P2. This is what is known as constant space, or O of 1. So that's the brute force solution. It takes O of n squared time, which is quite bad. Can you think of a more efficient way of doing this? And it's okay to use more space, we just want to decrease the time complexity. Let's see if you can come up with a way to solve this by scanning the array only once. That would make your solution O of n instead of O of n squared. So pause and think about it. Alright, so in CS14, you learn about the hash map. The hash map has keys and values. The point of a hash map is to store a key value pair and retrieve it in O of 1 time. For example, let's look at this hash map that maps a name to an age. In this case, name is the key and age is the value. If I were to ask my hash map, what is the age corresponding to the name Sam, it would return 23, and it would do it very quickly in O of 1 time. However, we don't always need to map a key to a value. Sometimes we just want to remember the keys. This is when we use a hash set. A hash set is like a hash map, except it only stores the keys. It doesn't map any keys to values. You can ask your hash set if the name Carl exists in it, and it would answer quickly in O of 1 time. In another example, you can have a hash set which keeps track of ages you've seen before. You can ask the hash set if the age 25 has been seen before, and it would answer yes here very quickly in O of 1 time. For both the hash set and the hash map, inserting only takes O of 1 time. Lookups only take O of 1 time as well. Therefore, hash sets and hash maps are extremely fast. The only downside is that they require extra space. So, in this case, which should we use right now? Should we use the hash set or the hash map? Well, let's first ask how we'd use either one. Remember, we want to find duplicates in an array. The idea is to go through each element in the array and somehow know if we've seen this element before. Which one of these data structures, the hash set or the hash map, fits the minimum requirements to remember if we've seen a number before? It's the hash set. We just want to remember if we've seen something before. We don't need a key value pair. We just need to remember the keys. In this case, the keys are the past seen integers. So let's iterate through the array and add each element to the hash set. However, if the element is already in the hash set, then we've found a duplicate. So let's think about the worst case input here. It's when we have to iterate through the entire array. This is the case when there is no duplicate, or the first duplicate doesn't occur until the very end of the array. Seen here is the case where we'd have to iterate through the whole array to find the first duplicate. Given that the worst input means we have to iterate through the whole array, what is the time complexity? It's O of n. And what is the space complexity? Well, in the worst case, we need to create a key in our hash set for every element in the array. If the input array somehow doubles in size, then we need double the amount of keys. It's a linear relationship. Therefore, the space complexity is O of n. Let's look at the code. Similar to the brute force method, this function is named hasDuplicate and takes in an array called nums. The first thing we do is create our hash set and call it hash set. Next, we set up the for loop to go through the array. Inside of the for loop, we check to see if the current element called num is already in the hash set. If it is already in the hash set, then we've found a duplicate and we should return true. However, if it's not already in the hash set, we should add it to the hash set. This way, in the future, if we ever see this element again, we'll know that we ran into a duplicate. Finally, we returned false if we make it outside of the for loop. This is because the for loop would have caught a duplicate if there was one. So, we've seen the brute force solution and also the hash set solution to solve this problem, and we've seen the big O time and space complexities for each. The brute force method takes O of n squared time, but only takes O of 1 space. The hash set solution only takes O of n time, but it takes O of n space. Is there something in between these? What if we need a solution that will solve this problem in less than O of n squared time, but also less than O of n space? Pause and think about this solution. Let's look at our array again. Imagine if somehow it was sorted. Since it's sorted, any duplicates in the array will be right next to each other. So now we can just check two numbers at a time and see if they're equal. This is different from the brute force solution because in the brute force solution, we checked all possible pairs in the array. But in this solution, we only check pairs of elements that are right next to each other in the array. As you can see, we will eventually run into duplicates if there are any. So let's look at the code. Just like the last two solutions, our function is called hasDuplicates and takes in an array called nums. the first thing we do is sort the array in place. By in place, I mean we don't take up any extra space to sort the array. You will learn about in-place sorting algorithms in CS14. However, if you've already taken CS14 and can't remember in-place sorting algorithms, I suggest you familiarize yourself with them after this video. Python has a built-in way to sort an array in place. So does C++ and basically every other language. This line sorts the array nums in place. Next, we create our for loop, where I starts at 0 and ends at the second to last element in the array. This detail is important. Inside of the for loop, we check to see if nums at I is equal to nums at I plus 1. Essentially, we're checking to see if the current element is the same as the element in front of it. This is why we stop iterating when I is the second to last element instead of the last element. Because if I were to iterate until it was the last element, then I plus 1 would be out of bounds. If two neighbors in the array are equal, we return true. Finally, just like in the past solutions, if we've made it outside of the for loop, that means that there were no duplicates. So what's the time complexity? Well, we need to scan through the entire array in the worst case, and that would be O of n. However, we sorted the array in the very beginning. The fastest sorting algorithm is O of n log n. Since O of n log n is larger than O of n, the big O for the entire algorithm is O of n log n. Now let's look at the space complexity. Remember that the sorting was done in place, so there was no extra space used due to the sorting. And we also didn't use any extra space to go through the array. So our solution is O of 1 space. Therefore, this solution is less than O of n squared time and also less than O of n space. To recap, here are the three solutions to this problem. They have their strengths and weaknesses. If you can't afford the space for a hash set, you should look into the in-place sorting solution. Here's a question I'll leave with you. Let's say you need the fastest possible solution. Which of these would you suggest?